Howdy, today on Flippin Science we're looking at drawing molecules. So molecular shapes are all linked back to a theory called Vespa Theory. It's called Vespa Theory even though it's pronounced, well, even though the letters make up VSEPR. So valence shell electron pair repulsion. The idea is that any pair of electrons is going to repel every other pair of electrons around an atom equally. So they're trying to get as far away from each other as possible. What that means is that you're going to get repulsion between all your bonding pairs of electrons, bonding and non-bonding pairs of electrons, non-bonding pairs of electrons, and single, double, and triple pairs. So what that means is all the electron pairs are trying to get as far away from each other as possible, and that leads to interesting shapes that we get. So to find the shape of a molecule, we need to figure out which is going to be a central atom, establish the number of bonding and non-bonding pairs of valence electrons around the central atom, and then establish the pattern of repulsion of those electrons, and that will lead you to your shape. The central atom is the atom which has the highest covalence, and the covalence just means how many bonds can it form. So carbon forms 4 bonds, nitrogen forms 3 bonds, and so on and so on and so on. If the central atom can expand its octet, you need to check the oxidation number first, and that will tell you how many bonds it can form. So we're going to do an example with HNO2. So we're going to identify the atom that has the highest covalence, and put the atom of highest covalence in the middle and distribute the other atoms around it symmetrically. Then we're going to draw in the number of bonds to satisfy the covalence. That might change our shape. And then we're going to draw in any non-bonding pairs of electrons, and then distribute the electron pairs symmetrically, and that will give us our shape. So the first thing we need to find out is which is the atom with the highest covalence. So we've got hydrogen, oxygen, nitrogen. Hydrogen can make 1 bond, oxygen can make 2 bonds, and nitrogen can make 3 bonds. So nitrogen is going to be our atom with highest covalence, so that's the one that's going to go in the middle. Next step, we're going to place the atom of highest covalence in the center and distribute the other atoms around it. Start with nitrogen here, we're going to have hydrogen down here, and oxygen up here, and an oxygen over here. So they're symmetrically dispersed around the nitrogen. Next step, draw the number of bonds to satisfy the covalence of each atom. Alright, so oxygen has 2, oxygen has 2, hydrogen has 1. There's a problem though. Our nitrogen has 5 bonds, so this doesn't work. So it can't be symmetrical like that. We have to have another arrangement. So the symmetrical arrangement didn't work, so now we're going to try a linear arrangement where we're going from one atom to the next to see if we can get our bonds working. So we're going to start here. Now we need to make sure we get the right number of bonds. So hydrogen wants 1 bond, oxygen wants 2 bonds, and now it's got 2 bonds. And nitrogen wants 3 bonds, 1, 2, 3, and oxygen wants 2 bonds. So now we're good. So each of the atoms has their covalence satisfied. Now you need to pop in any non-bonding pairs of electrons and distribute the electron pairs symmetrically. So to figure out non-bonding pairs of electrons, you take the number of valence electrons and you subtract away from that the number of electrons that are being used in bonding. So if we look at nitrogen here, nitrogen is group 5, it's got 5 outer shell electrons. 3 of those are used in bonding, so that leaves 2 left over. So there's 1 non-bonding pair of electrons around the nitrogen. So, oxygen has 6 outer shell electrons, 2 are being used, so 6 minus 2, so that means there's 4 electrons left over for each oxygen. So 1, 2, 3, 4, and 1, 2, 3, 4. Now we put those non-bonding electrons in, we can get a bit of an idea about the shape and how it's going to arrange itself. So we've got this double bond here counts as 1, so we've got 3 things that we need to repel as far away from each other as possible, so that gives us a trigonal arrangement, so there's a triangle. With the nitrogen we've got 1 non-bonding pair, 1 bonding pair, and the double there, they count the same, so that's going to be, again, triangular, trigonal. If we look at our oxygen here, we've got 4 things, so around that there's going to be a tetrahedral arrangement, but we've only got 2 bonding pairs, so it's going to look V-shaped over there. So now we can draw that. So we're going to start with the nitrogen here. Okay, so we've got the nitrogen, we've got a non-bonding pair of electrons, and we've got a double bond. I'm going to put the double bond going down this way, and I'm going to put my non-bonding pairs of electrons on the sides. So now we've got that triangular arrangement where we've got things 120 degrees away from each other. So now we've got a non-bonding pair of electrons. We need to put our bonding down to the oxygen down here. Putting my oxygen down here. And again, we've got our triangular arrangement here. So 1, 2, 3. So they're 120 degrees away from each other. And now we need to have our hydrogen, put our hydrogen in. I'm going to pop the hydrogen up here. My non-bonding pairs of electrons down here. So now we've got the tetrahedral arrangement. We've got 4 things. So one non-bonding pair down here, one bonding pair, one bonding pair, one non-bonding pair. So they're going to try and get as far away from each other as possible. So that leads to this kind of W almost shaped bendy molecule. Now remember, it will be 3-dimensional, so it won't look much like this in 3 dimensions, but on a flat plane that's what it'll look like. So we get angles going up here, down here, and then back up here. The bonding angles will be slightly different as we go along. The bonding angles don't matter for Year 12 chemistry, so don't worry about that. As long as you get the shape somewhat right, you don't have to know the angle in terms of degrees or anything like that. So we're going to do another example here with NaCl. So the first thing we need to do is figure out the covalence. So nitrogen wants 3 bonds, oxygen wants 2 bonds, chlorine wants 1 bond. So there we go. Place the atom of highest covalence in the center, so that's going to be our nitrogen, and distribute the other atoms around it. Cl on this side and the O on that side, so now it's symmetrical. Next step, draw on the number of bonds to satisfy the covalence of each atom. So chlorine wants 1 bond, oxygen wants 2 bonds, nitrogen wants 3, so there we go. Step 4, draw on any non-bonding pairs and distribute the electron pairs symmetrically. So if I do what I just had, so it looks a bit more like I know. Okay, so oxygen we had before, it's got 2 non-bonding pairs of electrons. Nitrogen, it's got a pair of non-bonding electrons, and chlorine has 6 non-bonding electrons. So 2 involved in bonding, the other 6 left over. So now that we look at that, we need to figure out what our arrangement is going to be. So the main thing is looking at what's happening at the central atom. So we've got a non-bonding pair of electrons, a bonding pair, and then a double bond. Each of those is repelling the others in an equal fashion. So that means we've got a triangular arrangement around the nitrogen now. So if we redraw it over here, we've got nitrogen here. We'll have a non-bonding pair of electron going down to our chlorine. We've got our double bond going over to our oxygen over here. We'll put in our non-bonding electrons around the oxygen. Okay, so we've got a triangle shape over here for our 3 things, so our double bond and our 2 non-bonding pairs of electrons. We've got a triangular shape over here, so from our non-bonding pair of electrons, our 1 bonding pair and then our double bond. Then we need to have our chlorine's non-bonding electrons here. They don't really make much of a difference. Okay, so now that we've got this arrangement here, we'd call that V-shaped. So it's a V-shaped molecule. Because of the non-bonding pairs of electrons here, we're getting repulsion between the non-bonding pair of electrons, the bonding pair of electrons, and the double bond over here in an equal fashion. So that leaves that V shape. So we'll do some other ones just quickly. So we'll start with COCl2. Okay, so carbon wants 4 bonds, oxygen wants 2, chlorine wants 1. So carbon's going to be in the middle. We'll start with carbon. We'll arrange the other ones symmetrically. We'll draw in our bonds, so chlorine, and oxygen wants 2, so that means we need to have a double bond up here. We need to put in our non-bonding pairs of electrons, so oxygen has 2 non-bonding pairs, chlorine has 6 non-bonding electrons, so 3 non-bonding electron pairs. And let's have a look at our shape there, and I think that's pretty much it. We've accidentally done it correctly. So we have a double bond here, a single bond and a single bond. They're each repelling each other equally, so we get this triangular shape. Because there's no non-bonding pairs of electrons around the carbon, this would be flat. So the shape we call that is trigonal planar. So it's triangular in shape, that's the trigonal, and it's planar, it's flat. We'll do the next one here. So this is Koro Methane. So if we look at our covalence, carbon wants 4 bonds, each hydrogen wants 1, and the chlorine wants 1 as well. So carbon is in the middle, and then we'll put the other ones around symmetrically. So chlorine, hydrogen, hydrogen, hydrogen. Drawing our bonds, so chlorine wants 1, hydrogen wants 1, hydrogen wants 1, hydrogen wants 1. You need to put in our non-bonding pairs of electrons. There's none for each of the hydrogens or the carbon there. And we've got 3 pairs around the chlorine. They don't really influence the shape. So we're left with this structure here. Now, the issue is, on a flat plane this is okay, but the world isn't flat, this is 3-dimensional. So what that means is we have to show that this looks a little bit tetrahedral. So we'll put the carbon in the middle, chlorine at the top, and then we'll have the hydrogens arranged like this down the bottom. The reason why we do that is it looks like this hydrogen is either coming out towards us or going back into the page. And that makes it look a little bit more tetrahedral. So this is how I would redraw it. You can put the non-bonding pairs of electrons around the chlorine if you like, but because they don't influence shape, you don't need to include them. So chloromethane has a tetrahedral shape. So today on Flippin Science we looked at drawing some simple molecules. That's it for Flippin Science today. See ya.